When we work out the value of something from an experiment, we know our value won't be the exact true value of the thing. And to give people an idea of how far off we might be, we estimate the uncertainty of our value. And this tells people the range we are reasonably confident the true value lies in. When we write it like this with units, remember, it's called the absolute uncertainty of the value as opposed to the percentage uncertainty. Note that I'm using OCR notation. AQA writes this and Edexcel writes this. Note that an absolute uncertainty must be rounded to one significant figure. The justification goes like this. If we're not even certain about this significant figure, it doesn't make sense to claim that we have any information about the next one. Students will lose the mark if they fail to round the absolute uncertainty to one significant figure. All three major exam boards expect students to estimate uncertainties in a range of ways. In exam questions, it's obvious which way they're meant to do it. In class, students have you to guide them, so don't worry about getting students to internalise everything that follows. The important thing, I would argue, is that they appreciate these estimates are not just some empty mathematical exercise, rather they reflect genuine ranges in which your values might lie, and so this force value is better than this force value. And so here is an overview of the different ways we're expected to estimate the uncertainty of a value. If the value is the stated value from the manufacturer, what's called the nominal value, then we simply take the manufacturer's estimate of the uncertainty, which is called the tolerance. An example where you will estimate the uncertainty of a resistance this way is when you're finding the capacitance of a capacitor in an experiment. You will use the value of the resistor in your calculations, but you won't actually measure the resistance yourself. This way of estimating the uncertainty of a value you don't do very often. Very common though is when we do have measurements and in fact have repeats and an average value. Then there's another way of doing it using the range. If we have only made a single measurement, no repeats, then it depends if the measuring instrument was digital or analog, and there's a way for each of these. Note that the stopwatch is treated as analog here because we consider human reaction times to decide the uncertainty rather than the measuring instrument. And finally, there are a few experiments where it's obvious from the outset that the range of values for a measurement is much bigger than normal because of a large amount of additional uncertainty introduced by our method. The classic example here is the whirling bung experiment, where you try to whirl the bung round keeping the radius constant, but the string is free to slide through the tube, so it's difficult to get even close. Realistically, you might decide the radius was potentially a couple of centimetres off your measured value either way, and in these situations you do just use your own judgment to estimate the uncertainty. The next set of videos will look at each of these ways of estimating the uncertainty of a value in more detail. If you're finding these videos useful, please subscribe and don't forget to check out our resources on the website and follow Learning Dojo on Twitter.